Hey there, in this video we are talking about pointers to structures in C++ programming and also enumerated data types kind of briefly at the end. This covers sections 11.9 to 11.12 in the Gaddis C++ book. So we had a whole prior chapter, chapter 9, introducing pointers and how they're useful and powerful and really important even in just how a processor just functions. Can you have a pointer to an integer variable? Yes. So the answer is also going to be the same for structures. And we should see what that looks like. So pointers to structures, obviously, a structure variable is somewhere in the memory system. It has an address. So you can get that address and you can store it in a pointer to that kind of structure. So pointers to structures are variables that can hold the address of a structure. So here's a declaration right here, right? And you might ask yourself just for a second, clearly a variable is being declared. What is the type of that variable? It's a student pointer. The type is student pointer. And the name of that variable is stuPointer, right? Again, which is short for a student pointer, which is what we're talking about. Occasionally I've seen a couple of students think that you need to name your pointers PTR. Hopefully you realize you can name them whatever you want, give it a good identifier, but we want it to be descriptive. So certainly a lot of the examples in the book, it makes sense to call it a whatever pointer because that clearly describes what it is. But the type here is student pointer, and of course the name is stuPointer. Now you're likely to see this when dynamically allocating a structure. I don't think we have an example of that in these lecture slides, but the next thing you could do is you could say stuPointer equals a new student, right? And it dynamically allocates, like we've talked about before, one of those things in the heap memory, or you could do that for a whole array. Right? You could ask for a new student array sized 5,000. And that is what your operating system will go find that much memory for you and save it in a pointer. Or if you're passing a large structure to a function, particularly if you're working on maybe slightly older code, at a prior point in history, C++ didn't have this notion of reference variables. And so originally you just had to pass a pointer to where your variable was. And nowadays we have this reference syntax, which really just does the same thing. But you might possibly see the actual pointer syntax being used instead. I know that when I was working as a software engineer all day long, I was seeing hundreds and hundreds and hundreds of pointers being passed into and out of functions for structures. Okay, now a little interesting piece of syntax here. When you have a pointer, and you want to get at the members in that memory location, right? What's that going to look like? To access a member, well, obviously you've got to dereference the pointer to actually be looking at the actual structure itself. Then you've got to identify the right member field. So you're going to use a star to dereference the pointer, obviously, and you're going to use a dot to get at the particular member field, again, obviously. The little bit of the complication is in the C++ order of operations. Okay, the dot operator, which you actually want to happen second, based on what we just said, has higher precedence. So by default, it actually happens first, versus the star operator, which we just said we want to happen first, but the order of operations would have it happen second. Okay, that's not the order we want. So in order to make that work, you would have to use parentheses, right? You have to do this. So here I've got that student type structure called stuPointer, student pointer, student structure pointer called stuPointer, right? And so you want to dereference that first. You got to put that in parentheses to make that dereference happen first with the asterisk. And then after that, you can put down dot student ID to get into that particular member field. That's what that would have to look like. So a little bit awkward, right? A little bit awkward looking. Because of that, C++ has a second way of doing this. It looks a little bit neater on the screen. You can use this short arrow syntax, and that's the dash greater than symbol, right? It looks like an arrow that does both of those jobs. So if I have a pointer called stuPointer, and that type of thing has members called student ID, I can write down stuPointer arrow student ID. And that arrow does both of those jobs. It dereferences the pointer, right? Goes to that memory location, and then it digs into that particular member field, right? And so I'm used to seeing that in lots and lots of codes. I've got a function, and here's a pointer coming into like a big structure that we didn't want to copy. I need to get the different member fields, and I use this arrow to do that. Dereference the pointer and dig into this member field. So hopefully that I can see why they use that syntax, is it's literally looks like a pointer. It's like, you're going to be aiming over there at that particular member field in that structure. So go over to that location and get that member field, is what that's saying. You know, if this issue of the order of operations, if you want to see the full story, the book has an appendix C, it might be appendix B or C, that has a list of the full order of operations of all the operators in C++, and there are about 50 of them. You know, like normal arithmetic, there's only 4 or 6 depending on how you count it. But of course, C++ actually has 50 different operators, and there had to be a decision about what the order of operations was. So it was considered that the dot operator was more important than the dereferencing asterisk operator, but then it winds up kind of being opposite what you really wanted. But then we have this arrow syntax to fix that for us. So that actually looks very nice. You know, again, think about how this relates to digging into more detail, right? When you have a large structure, you say the thing at the top level, and you dig into more detail and dig into more detail, kind of like when you have structures in an array. You have to name the array, name which number you want, and then dig into the field. And similarly here, right, you're digging into the particular field, which constitutes more detail to the data that you're talking about. So I kind of like that syntax, actually. Here's an example of a function that uses that. So we have sounds like an input function to me called getData. And, you know, so we've seen some examples in the past for input functions that used structure return values. I actually kind of prefer this example in the book myself. So I've got an input function that is of type void, and you're going to pass in a structure to be filled out. Could have been by reference. Here they're doing it with a student pointer. So here comes an argument, just one. It's of type student pointer, and they're calling this S for short. So here we're going to prompt the user for the student's name, and you use getLine because it's a string, possibly with spaces, and you put that result, you put that input into S arrow name, right? Dereference the S pointer. Now you've got an actual structure, put it in the name field. And you send in the student ID number into S arrow ID num, and the hours enrolled gets put into S arrow credit hours, and the GPA gets stored in S arrow GPA. Okay, so pointer to a structure to a piece of member data. And at this point, the S structure is entirely filled out, and whoever called you can go, you know, look up what got stored there, right, via that pointer. So this is, we don't have too many examples of that in the book, but in my professional experience, I'm used to seeing lots and lots of functions that look like this, actually. So I'm very familiar with that arrow pointer myself. And let's test this program 11.8 here. Again, I have the classes tab up in Dev C++, so I can kind of keep an eye over here on the definition of the student structure. It's got all the members, got all the types there. And if I happen to be working, like the interesting thing really here is this getData function. So if I happen to be working down here in the getData function that takes a student pointer, and I got to remind myself, what are the members of that structure? I can just look over here and go, let me see, get the name, get the ID num, get the credit hours, get the GPA. Yeah, that's everything in that structure. I haven't forgotten about anything. I'm not leaving any of the members uninitialized with garbage data. So that's handy to see that classes tab over here. If I don't want to see that, I can just collapse it. I kind of like that. So let's test this and make sure that input function actually works. So I think we're in this input function right now, and we were handed a pointer to a student structure, of course, and we're filling out all that data. So maybe the student's name is Alice Smith. She's usually my first example, and her student ID number is 3456, and her credit hours enrolled, maybe 12 perhaps, and her GPA is 3.7 because she's doing pretty well. Great. So that structure was filled out and was handed back to the main function. And then the main function actually printed all that stuff out. Here is the student data you entered. And that all looks correct. So it looks like that succeeded at saving that information in the structure that we got here via the pointer. And that totally works. Don't forget about that arrow syntax, which is how you're accessing the members off that pointer there. And so again, that's a pretty well structured program. I like that. Again, I prefer this kind of system of your input functions taking a reference or a pointer to a structure you're going to fill out. And then I leave my input functions void, just like this example from the book. So I like that quite a bit. Now, now we have a couple things that could possibly get combined in different ways. The dot operator and the asterisk, and if there's parentheses and if there's not, and there's the arrow that's an alternative. So any one of these, will compile and work. So you might want to be familiar or at least be able to decipher what's happening here. Here's a table out of the book of different possibilities. So S arrow M. For that to make sense, the S has to be a pointer. And it has to be a pointer to a structure with a member field called M. And if that's the case, then this will compile. And that says dereference S, go to that structure, look up member M. And of course, and then you can syn to it or count it or use an arithmetic, whatever. But that's what that would have to be. Now, looking at this star A dot P. Now I know, remember, the dot has higher precedence than star. So if there's no parentheses, the A dot P has to happen first. So the A has to be an actual structure, not a pointer. The P has to be a member field in an A structure. And then if there's this asterisk here to dereference that, that only makes sense if the P itself is a pointer. So I have a structure A, it's got a member called P, that thing's a pointer, and then you're going to dereference that, is what that is. Now here, okay, so here the dereference happens first. So the S has to be a pointer. Got it. If you dereference that, I guess S has to be a structure, and it has to have a field called M. Got it. So go to the structure, go to this pointer S, dereference it, go to that structure, get this member field M. So notice that that actually is the same as S arrow M. We said that on the prior slide. That's the whole point of the arrow, is to shorten this slightly ugly piece of typing. Now this one here. Okay, so so for this to make sense here, S has to be a structure pointer because the dereference is going to happen. And then it has to be pointing to a structure that's got a field called P, and that also has to be a pointer for this stuff to make sense. So yeah, S is a structure pointer, P is a member of it, it's also a pointer. So this expression is going to access the value pointed to by P. So the arrow happens first, to be clear, right? The S arrow to P, that actually happens first because that's got very high order of operations. P would have to be a pointer, and then you dereference that P once you got it. Now here, think about this. Okay, star parentheses star S parentheses dot P. Okay, so clearly star S happens first. So S would have to be a pointer to a structure. You dereference that, then this P happens next. Outside the parentheses, remember period, the dot has higher order of operations than star. So you dereference this, that has to be a pointer. This dot P itself has to be a pointer, and then you get at that, and then you dereference that pointer. So again, S is a pointer to a structure that has a field called P, which is a pointer, and you dereference the S, get the member field, and then get the P and dereference that. So for what it's worth, that's the same as the prior example, star S arrow P. You can kind of think through those examples. So it can get a little bit, possibly a little tricky. This would make for a great test question. I bet on my next test, there'll be 1 or 2 questions like this about what's happening in these different cases. So based on where the arrow is, or the star is, or the dot is, the parentheses, only one thing makes sense, right? If you're dereferencing something, it had better be a pointer. If you have something after a dot, it had better be a member field in a structure. So you can kind of decode what these things would have to be based on that syntax. And that makes for a great 1 or 2 test questions on my next exam. All right, so totally different subject. So, the theme of chapter 11 has been making new data types. Remember, when you make a structure, you've made a fully formed new data type, just like int, float, char, bool, string, whatever. And anything you do with that stuff, with an int or whatever, you can do with your structures. Into a function, out of a function, into an array, pointers, dynamic allocation, whatever you want. So on that larger story, not talking about structures right now, but on that larger story of making new data types, here's another fairly common way that C++ programmers make new data types. These are called enumerated data types, or enums for short. So an enumerated data type is another programmer-defined data type. Again, you're making new types. But this consists of specific discrete values called enumerators, which basically represent integer constants. You know, we've had examples in the book previously of like maybe you have a menu with a bunch of options in the menu, and we've been setting up a bunch of constants. So I think there's an example of a health club membership, and the user has to pick, am I an adult or a senior or a child? And the menu says press 1 for a child and 2 for an adult and 3 for a senior. And we made constants for const int adult choice equals 1, and const int child choice equals 2, and constant senior choice equals 3, or whatever the order is. So that got a little bit repetitive. It's kind of sort of the same typing over and over again. And in those kinds of cases, we would like a shorter way of doing that. And that's what an enumerated data type is for. Let's see that. So here's an example. There's a keyword called enum, which is short for enumerated types in C++. So you'd write down enum, and here I'm making a new type. Right? It's not int float char bool, it's not a student, but the new type is day. And in curly braces, you indicate all the values that a day could possibly be. And here I've listed Monday, Tuesday, Wednesday, Thursday, Friday. We wrote it all caps because these are basically integer constants. And what the compiler does behind the scenes is the same as it made a constant integer called Monday and set it to 0. It made a constant integer Tuesday and set it to 1. Wednesday is really the number 2 in disguise, and so on and so forth. So now you have this type, okay? And this would, again, this saves you some typing, saves you some reading, versus a whole bunch of different constant integers that are just like one thing at a time. So we commonly use that. Now, of course, it's a new type. Can you declare a variable of type day? Yes. Can you pass an argument of type day into a function? Yes, and like all the other questions. So let's see an example of that first thing at least. Yeah, you can declare a variable of type day. So I could declare a type day variable called today, and then I could assign it Thursday. Right, it was really the number 3 in disguise, if I'm right. Yeah, number 3 in disguise. So to be clear, and you get a safety feature here, because such a variable can only be assigned values from the enumerated list. So I can set today to Thursday, and that works. But if I try to set today to the number 10, even though I know mentally that behind the scenes it's really an integer, the compiler won't permit that. So you get this extra safety feature whereby if I have a day variable, it can only receive one of those enumerations, specifically Monday, Tuesday, Wednesday, Thursday, or Friday. That's it. Even if you try to set today equal to 3, that won't work either. You've got to write the specific enumeration name. So again, this is one of these things that seem restrictive at first glance, but if I'm working on a really big program with a really big team, I don't want to have to trust that Bob, Kathy, Dennis, Ernie, and Frank never ever get hazy and set the number 10 to my day variable. So the compiler will protect me from that and only allow legitimate enumerations to be set into this variable. So it's much more secure and easier to communicate and enforce what it's supposed to be doing in a bigger program. Now, this is just the tip of the iceberg, okay? There's a much larger story of enumerations and things you can do with them. So if you look at that last section in chapter 11, it's actually a fairly big section with lots and lots of things you do with enumerations, and you can read that on your own. But I think this is really all we need for the lectures for our class, is the basic idea of enumerations, is it's really a bunch of integers in disguise with safety features. So you'll see that in code. It's pretty common. And that's the end of chapter 11 for us. So working with structures and maybe even enumerations, the main idea is now we are able to define our new types by putting together fundamental variables in interesting ways. And I kind of think of this like chemistry. You know, our fundamental data types of int, char, bool, and float are kind of like atoms. And now we're kind of doing chemistry of putting them together in larger molecules to do more interesting stuff. And you're building with bigger pieces, and you're going to be more efficient as a programmer because instead of 4 or 5 things being passed into a function, it's just one thing, namely the structure. And one thing coming out can be a whole package of data. And you can put them into an array, of course. And you're getting a lot of punch for just a little bit of typing, and it's going to look very short on the screen to read and understand. And that is what we really want. So I would recommend that you read book chapter 11 and see more details on all that stuff. There's a whole lot of more examples, of course, that we didn't have time for here. Test yourself with the review questions at the end of chapter 11 in the Gaddis C++ book. And of course, my students will have a programming challenge in chapter 11, and I'm pretty sure they're going to have a program that's going to have an array of structures. And as always, we need a modular program with separate functions for input and processing and output. Of course, that's the case. And my students can look up on the learning management system exactly what the assignment is. But before that happens, we would do this lab here. And this is one of the biggest labs that we do in the semester, as a matter of fact. So if we have time, maybe we can do this in an hour. We try to write a whole program from scratch called the airport structure array. And what this says here is write a program that uses a structure to store the following information for a particular month at the local airport. So the structure has total planes landed in that month, total planes departed in that month, and the maximum planes landed in any one day in that month. Okay, so structure with 3 things in there for 1 month's information about the airport. Now the program should declare an array with 12 of these structures, so an array size 12 of the airport info stuff to hold information for the entire year. And the program should prompt the user to enter data for all 12 months, right? And then the program should calculate and output the grand total, how many planes landed all year, the average number of planes landed per month, and also the maximum number of planes that landed in any one day for the whole year. So a total, an average, and a maximum type job, which are all those fundamental algorithms that you do with arrays that we reviewed back in chapter 7 of our course specifically. And of course, each task should be done in a separate function to have a nice modular program. Now, this is something you can do on your own, right? Even if you're not my student, even if you don't have the book, you can totally do this on your own. So it's a more sizable project, honestly. But if you're one of my students, we will, working together, we will try to do this in an hour. I'm not sure we're going to get the whole thing done. Sometimes we get some of these functions done and I have my students finish it outside of class. But a really good exercise and a really good project for more practice. Now, the difficulty that we're starting to have is that as we have larger structures, we're building with bigger pieces, and we love that. As we have larger structures and we're putting it in large arrays, it takes a long time to test this. So once I write this program, or even once I write one of the functions at a time and try to test it, technically, this program requires, okay, so the structures have 3 pieces of data each, and I've got 12 months. Well, that's 36 separate things. So just to test this program once, I have to sit here and I have to type in 36 different pieces of information just to see in one single test case whether the program's working correctly or not. So that's starting to be inefficient in taking more and more time just on the testing aspect to get all that data in. So it's going to be a little bit repetitive. It's not good. So wouldn't it be nice if there was some way to get the computer to enter all that input automatically, maybe from something stored on the hard drive, like maybe a file? That would actually start to save us a lot of time on the testing aspect. Well, that's what the next chapter is about. So when we come back next time, we're going to start in on chapter 12 about file operations, saving lots of data in files in your secondary storage, a USB or a SSD or a hard drive, right? And getting your program to automatically read all that information instantaneously. And then we could possibly use that to speed up our testing cycles of having the program get all the information from a file instead of us typing it repetitively as human beings. So that's another tool that we really ought to have in our toolkit to make our development go faster. So I hope that that sounds promising for next time, and I'll see you then.